So myself, I am Varad Daoo, a doctoral student at the Department of Chemical Engineering, IIT Kanpur, right? And so in the last class, what we have seen? We have seen about the dual nature of matter. First of all, we have seen the limitations of Bohr models, and one of the limitations of Bohr's model was that it could not explain the dual particle and wave-like nature of atom, subatomic particles, and hence that was one of the major drawback of Bohr's model, and hence then we delved into this what is the dual particle nature, dual particle and wave-like nature. Then we studied some experimental results which supported the experimental which suggested that atom is a particle, atom shows particle like behavior, while we have while other also we have while we also saw about the experimental results such as interference and diffraction, which showed that it is a wave-like nature. So we studied about this dual particle wave-like nature, and then further we discussed about the de Broglie relationship, and we showed that there is a wavelength associated with every object in the universe, and the this wavelength, however, for some for massive objects like macroscopic level objects, this wavelength is less, and for subatomic particles this wavelength is huge, and hence at macroscopic level we see the particle nature is dominated because the wavelength is less, whereas at the subatomic or atomic level the wavelength characteristics dominate over the particle nature because of the wavelength, larger wavelength, right? So now so in today's class we are going to see about this de Broglie relationship in detail. Then further also we are going to study about the Heisenberg uncertainty principle. Then we are going to solve a couple of examples. And then at the end, if the time permits, we are going to delve into quantum mechanics, slight introduction to quantum mechanics, right? Structure of atom, lecture 11, right? The first topic which we are going to study is derivation of Bohr's postulate, right? Of quantization of angular momentum from de Broglie relationship, right? So de Broglie equation help us in explaining the Bohr's postulate regarding the quantization of angular momentum of an electron, right? Now let us consider an electron moving around the nucleus in the form of wave in a circular orbit of radius r, right? So let me drag a picture. So let us consider that the electron is moving in a circular orbit. So this, let's say this is the circular orbit, right? Consider an electron moving around the nucleus in the form of wave, right? In a circular orbit of radius r, right? So let's say the radius is the r, right? The wave train of electrons may be continuous. So the wave nature could be in a continuous. So this is an electron wave with in phase, right? In phase electron wave, where this is out of phase electron wave, right? In phase, out of phase, right? And this figure represents the representation of electron waves and orbit in phase. So this is in phase and this is out of phase. If the two ends of the wave meet to give a regular series of crests and troughs, then the wave is said to be in phase, right? So this is a wave in phase. If the two ends do not meet to give a regular series of crests and troughs, it is said to be out of phase. So this is out of phase, right? As evident from this figure, right? From this figure, for wave motion to be continuously in phase, the circumference of circular orbital, right? So the circumference of the circular orbit must be an integral multiple of number of waves, right? Otherwise, the wave would interfere destructively and cannot and cancel each other and thus destroy itself, right? Therefore, by considering the electron as wave, we automatically impose a limit to the number of orbits, right? Let us write this down from figures present in next slides, right? We conclude that for by considering electron as wave, we automatically impose a limit to the number of orbitals, number of orbits, sorry, right? It is clear that the circumference of the orbit, right? Circumference of the orbit must be integral multiple of the electron wavelength, right? Right? So in other words, mathematically we can define that 2 pi r should be n lambda, right? This is the circumference and this is the integral multiple of electron wavelength, right? Lambda is equals to electron wavelength. From de Broglie relationship, what we have? We have lambda is equals to h by mv, right? Where h is the Planck's constant, m is the mass of electron, right? What does this mean? Right? So we substitute what we get 2 pi r is equals to nh by mv, right? That means mvr is equals to nh by 2 pi, right? Sometimes this h by 2 pi is also called as h cross, right? So mvr is nothing but n into h cross, where h cross is h by 2 pi, right? What can we draw from this expression is the angular moment of an electron should be an integral multiple of h by 2 pi, right? In other words, the angular momentum is quantized. This is the same as Bohr's condition for quantization of angular momentum, right? So what does we conclude from here? We conclude that thus the angular momentum of the electron should be an integral multiple of h by 2 pi, right? What does this mean? In other words, the angular momentum is quantized. This is same as the Bohr's condition of quantization of angular momentum of fixed energy orbits. Now let us discuss about the number of waves in nth orbit. By definition, we know that this is going to be equal to circumference of the nth orbit divided by the wavelength, right? Which is nothing but 2 pi r by lambda. But we know that this must be an integral multiple of, right? So first we use de Broglie's wavelength. Lambda is equals to nh by 2 pi, right? So we substitute it here nh by 2 pi, which comes out to be r by, right, h by mv. Sorry, this is h by mv, right? Is h by mv, which is nothing but what? 2 pi into mvr by h, right? But we know that mvr is nothing but mvr is equals to nh by 2 pi, right? Just now we saw, right? mvr is equal to nh by 2 pi, right? Hence, when we substitute, what we get is 2 pi nh by 2 pi divided by h, which is nothing but n. Hence, number of waves in nth orbit are nothing but the n value, right? This is very important, right? So now let us discuss about distinction between electromagnetic waves and matter waves, right? Distinction between electromagnetic waves and matter waves. So here we are going to write electromagnetic waves, matter waves. The first point is electromagnetic waves are associated with electric and magnetic fields perpendicular to each other and to the direction of propagation of radiation, right? Whereas matter waves may not be associated with electric and magnetic fields. So electromagnetic waves are associated with electric and magnetic field perpendicular to each other and to the direction of propagation of radiation, right? Whereas matter waves may or may not be associated with this. Matter waves may not be associated with electric and magnetic field. The second point is that electromagnetic waves can be radiated into space or emitted, right? Matter waves are neither radiated into the space nor emitted by the particles, right? These are simply associated with the particles, right? So electromagnetic waves can be radiated into space or emitted. Matter waves are neither radiated into the space, emitted by the particles, right? They are simply associated with the waves. They are simply associated with the particles. Electromagnetic radiations or waves versus matter waves. Third point is going to be electromagnetic waves do not require any medium for propagation. That is, these waves can pass through vacuum, whereas matter waves require medium for propagation. That is, these waves cannot pass through vacuum. Do not require any medium for propagation, whereas these require medium for propagation. Fourth point is all electromagnetic waves travel with the same velocity, whereas matter wave travels with different velocities. All electromagnetic waves travel with same velocity, okay? Matter waves travel with different velocities. Right? The velocity of all the electromagnetic waves is right with the same velocity, and the speed is that velocity is nothing but speed of light meter per second. Right? The wavelengths of electromagnetic radiations are much larger and are given by normal radiation that lambda is equal to c by v, whereas for matter waves we have uh, probability relationship, right? So the wavelengths of electromagnetic radiation are much large and are given by the relation lambda is equal to c by mu, right? So mu is the frequency, right? Whereas matter waves have shorter wavelengths given by de Broglie relationship, right? H by m, right? Now we are going to study about the Heisenberg's uncertainty principle, right? So far, we have been believing that anything can be specified to any desired degree of accuracy, right? However, Heisenberg in 1927 put forth the principle known as Heisenberg's uncertainty principle, right? So, the definition of this Heisenberg uncertainty principle is it is not possible to measure simultaneously both the position and momenta of a microscopic particle with an absolute accuracy, right? So, this is the statement of Heisenberg's uncertainty principle, which states it is not possible to measure simultaneously both the position and momentum are called as velocity of a microscopic particle right, with absolute accuracy, right? Right? So mathematically we can say maybe expressed that maybe expressed as delta x for this delta x multiplied by delta p greater than equal to h by 4 pi, right? Where delta x is nothing but uncertainty in position, whereas delta p is nothing but uncertainty in momentum, right? The sign greater than or equal to here means that the product of delta x, right? So the product, so this sign means that the product of delta x and delta p, it can never be less than h by 2 pi, right? That means even in best case it cannot be zero, right? It always has to be greater than some particular value, right? And the consistency of the product of uncertainties means that if delta x is small, right, then the position of the particle is measured accurately, then delta p would be large, right? That is, there would be large uncertainty in its momentum. On the other hand, if delta p is small, the momentum of the particle is measured more accurately, whereas delta x would be more, right? That would be a larger uncertainty with regard to the position of particles, right? In other words, if the position of particle is measured accurately, there will be more error in the measurement of momentum, and conversely, if momentum is measured more accurately, the position will not be accurately known, right? So let us write it in here. So what we get from here is, in other words, if the position of a particle is measured accurately, right, then there will be more error in the measurement of momentum, right, and vice versa, right? So because delta p is nothing but m into delta v, we can also say that delta x into m delta v is nothing but has to be greater than or equal to h by 2 pi, right? And when we take this m to the other side, this means that delta x into delta v greater than equal to uncertainty principle. So this is in the form of momentum, right? Because delta p is here, and obviously we don't have any uncertainty in the measurement of mass, right? So when we write delta p as m into delta v, we just take the m to this side, and we have uncertainty in the position multiplied by uncertainty in the velocity has to be greater than or equal to some positive volume, which is h by 2 pi m, right? So this also means that the position and velocity of an object cannot be simultaneously known with accuracy. This is true only for the subatomic particles, right? This also means that the position and velocity of an object cannot be simultaneously known with accuracy, right? So now let us try to understand the physical concept, right? The physical concept of uncertainty principle. Physically, what does this mean? Uncertainty principle. Now, in order to understand this, let us take a. So, in order to understand the physical concept of uncertainty principle, let us study as to how the position of a material object is determined, right? To determine the position of an object, we must be able to see the object, right? This can be done with the help of light of suitable wavelength, right? When the beam of light falls on the object, right? This is the object, and this is the incident photon. When it falls on the object, right, and the reflected ray enters our eye, we get to know about the position of the. We get to know about that part of the about that object, right? Now, if the object is large, its position and velocity will not change by the impact of striking photons, right? Thus, it will be possible to determine both the position and velocity of the object simultaneously. However, in the case of microscopic objects such as electron, the interaction of striking photon of light with particle will cause appreciable displacement of the particle from its normal path, right? So this was the original. This was the original path of electron. Had the incident photon not been hit by it would have continued to go in this path. It would have continued to go in this path, right? Because the incident photon interacted with this electron, and because of the collision between this incident photon and electron, the electron changes position from this path to this path. Why? Because the interaction between those two things is of comparable nature. Had this been a microscopic object, in that case, the incident photon collision of these two things would not have caused so much of difference, right? But because of subatomic particle, this uncertainty remains, right? However, in case of microscopic objects such as electron, the interaction of striking photon of light of the particle, right? The interaction of striking photon of light with the particle will cause appreciable displacement of the particle from its normal path, right? Hence, as a result of this, the particle undergoes a considerable change in its path and velocity due to the impact of single photon used to observe it. Thus, the very act of measuring the position of microscopic particle causes a change in its momentum, right? So this figure, right? So this figure shows us the how the position of an electron changes by the impact of photon, right? The collision of photon with the electron sends in an unprecedented direction, right? Thus, it is not possible to determine simultaneously the exact position and momentum of the electron or any other microscopic object, right? Now, let us understand the significance of uncertainty principle in our daily life. So, one of the important application of the Heisenberg's uncertainty principle is that it rules out the well-defined circular orbits, right, or trajectories proposed by Bose. Uncertainty principle rules out the well-defined circular paths or orbits proposed by Bose. Right? Since the subatomic particle, like an electron, it is not possible to simultaneously determine the position and velocity at any moment with good degree of precision, right? Therefore, it is not possible to talk about the trajectory of an electron or well-defined circular orbits. It should be borne in mind that the uncertainty principle is not due to the lack of sufficiently refined techniques, but it is due to the fact that we cannot observe microscopic things without disturbing them. no microscopic things, right? No instrument can observe the position of an electron without affecting its motion. In other words, uncertainty principle is the fundamental limitation of nature, right? So, uncertainty principle is the fundamental limitation of nature, right? Thus, we cannot design an experiment to obtain an accurate value of both position and momentum of microscopic object. However, in our daily life, this principle has no significance, right? This is because we come across only large objects, right? That is the objects which we can observe with naked eye without altering their position, right? Without altering their motion. The position and velocity of these objects can be determined accurately because in these cases, during the interaction between the objects and the measuring device, the changes in position and velocity are negligible, right? Okay. Now we are going to solve couple of sample examples, right? So first question is a tennis ball of mass 6.0 10 raised to power minus 2 kg is moving 62 meter per second, right? Calculate the wavelength associated with this moving tennis ball. Second question is, will the movement of this ball exhibit a wave character? Right? Basically, what we are asked to find, we are asked to find the de Broglie wavelength. Right? So, according to de Broglie, we know this is nothing but h by mv. For problem at hand, so this is the Planck's constant, right? And we know the mass of the particle is tennis ball is 10 raised 6 into 10 raised to power minus 2 kg and velocity is 62 meter per second. Lambda comes out to be around 1.8 10 raised to power minus 34 meter, right? So clearly this is very less, right? This wavelength is too small to be measured and thus therefore the wave nature of ball cannot be detected. Wave nature of ball cannot be detected, right? Thus the ball will not have wave-like character, right? Let's move on to the next question. Question number 2. A golf ball has a mass of 40 kilograms and a speed of 45 meter per second. Right? If the speed can be measured with an accuracy of 2%, calculate the uncertainty in position. So here we are going to use uncertainty principle, right? So we are given uncertainty in the velocity is nothing but 45 meter per second, right? Which is nothing but sorry, this is the velocity, right? Sorry, this is the velocity, right? And uncertainty has been given by what? Uncertainty is given by 2%, right? That means uncertainty is nothing but 0.02 multiplied by this 45, which comes out to be 0.9 meter per second, right? And we know Heisenberg's uncertainty principle. According to that, delta x into delta v greater than equal to h by 4 pi m, right? This means delta x has to be greater than equal to h by 4 pi m into delta v, That means delta x has to be greater than or equal to 6.626 10 raised to the power minus 34 divided by 4 3.14 into m, right, which is 40 kg. 40 into 10 raised to the power minus 3 kg, right, multiplied by 0.9. Hence delta x comes out to be around greater than or equal to 1.46 10 raised to the power minus 33 meters, right. This is the uncertainty in its position, right. So now we are going to talk about the short introduction to quantum mechanics, right. So quantum mechanical model of atom and concept of atomic orbital. So the wave character of an electron and the uncertainty in its position and momentum gave a serious blow to the Bohr's model of an atom, right. So according to Bohr, the electrons revolve around the nucleus in certain well-defined circular orbits, right. But the idea of uncertainty in position and the velocity overruled Bohr's picture of fixed orbits. Thus, the classical mechanics could not describe the behavior of electron in atom correctly. Therefore, the scientists started looking for a model which could incorporate the dual nature of matter and the uncertainty principle, right? And this resulted in a new approach called as quantum mechanics or wave mechanics, right? To overcome Bohr's model limitation, a new approach called quantum mechanics or wave mechanics was created, right? This is a branch of science that takes into account the dual behavior of matter. The quantum mechanics is a theoretical science which deals with the study of motion of the microscopic objects like electrons, which have both observable wavelength particle and properties. Okay. So, quantum mechanics is a theoretical science which deals with the study of the motion of microscopic objects like electrons, which have both observable wave-like and particle-like properties. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. On the basis of quantum mechanics, Schrödinger proposed a model of an atom which considered wave-particle duality of matter and Heisenberg's uncertainty principle. This model was known as quantum mechanical model of atom. Right? In 1927, Erwin Schrödinger described the wave motion of an electron in three-dimensional space around the nucleus by a mathematical equation known as Schrödinger's wave equation. Right? And the Schrödinger wave equation is given by this expression: del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus 8 pi square m by h square into e minus v of psi, sorry. This is Schrödinger's wave equation, right? Where psi is the amplitude of the wave, x, y, z are the coordinates of position of electron, coordinates of position of electrons, and A is the total energy of electrons. V is the potential energy, right? So V is the potential energy. M is the mass of electron, and H is the Planck's constant. Mass of electron and H is nothing but Planck's constant. This simple equation, right? This complex expression can also be written in a simplified manner as following, which is H psi is equal to E psi, right? H psi is equal to E psi, where H is the Hamiltonian operator, and the solutions of Schrodinger equation wave gives E and psi. The solution of Schrodinger's wave equation give E and psi. Although the Schrodinger wave equation was difficult to accept at first, it has now gained wide acceptance, right? This is because the result obtained from Schrodinger wave equation are in excellent agreement with the experimental findings. One of the major achievements of Schrodinger wave equation are that it successfully incorporates the experimental information about atoms and molecules. So this is where we end our today's class, right? So in today's class, what we have seen is uh, we have seen about the Heisenberg's uncertainty principle, right? And then we have seen that why the Heisenberg's uncertainty principle exists and why it is dominating at macroscopic scale, right? Then we have also seen the significance of uncertainty principle in our daily lives. Further, we have solved some couple of examples, right? And at the end, we have a little bit touched upon the quantum mechanical model of an atom and atomic orbitals, right? So so I thank you all for attending this class, and I hope to see you again in the next class. Thank you.